So now we're going to start talking about logarithms and logarithmic functions. Logarithms basically, or can, allow us to talk about some funky exponents. So let's say, we know that 5 squared is 25, right? And we know that if we do 5 to the third, if we multiply 5 by 5 by 5, we're going to get 125. But what about, if we want to get 100? What would we raise 5 to get 100? Well, since 5 squared is 25 and 5 to the third is 125, it has to be that this number would have to be between 2 and 3, right? Since 100 is a number between 100 and 125. What is that number? It's some crazy decimal number, but in math, we always need notations to represent those crazy decimal numbers. And so, if I want to know, or if I want to represent the power that 5 must be raised to get 100, I will say log base 5 of 100. Okay? This mathematical notation represents the power 5 will be raised to get 100. So our logarithmic notation, what is a log? For any positive real number b, and b is not equal to 1, and any positive real number x, log base b of x represents the exponent that the base b, this is called our base, and our base is always written as a subscript, okay? Always, and that's very important, always written as a subscript. And x, this number here, we call that the argument of the logarithm, okay? So log base b of x represents the exponent that our base b must be raised to in order to get our argument x. So, if you see that log base b of x is equal to a, this also says that if I take b to the a power, I'm going to get x, right? Log base b of x represents the power b has to be raised to get x. If I say that power is a, I'm saying that b to the a power is x. And so this is some really powerful notation. And we'll see how knowing the equivalence of these two statements is going to allow us to solve some equations that we may not have otherwise been able to solve. So this is what we would say with logarithms, and this is how we would say the same thing with exponents. So if I want you to evaluate log base 5 of 125, remember the log represents the power you raise the base to in order to get the argument. So to evaluate this log, you have to basically find out what 5 must be raised to get 125. And so if you don't know that off the top of your head, then get out your calculator and start raising 5 to some powers. So if we do 5 squared, we get 25. If we do 5 to the third, we get 125. Oh, so it must be that if I take 5 and raise it to the third power, I'm going to get 125. Therefore, log base 5 of 125 is 3. Because 3 is what I have to raise 5 to get 125. Okay, doing the same thing here. Evaluate log base 2 of 1 over 32. So this is, if I'm wanting to find out what this is, right? my log is the power I raised 2 to get 132. So I have to figure out what I would raise 2 to get 1 over 32. So kind of taking a step back here, I know if I do 2 to the 5th power, then I get 32. And if you remember what we talked about with negative exponents, therefore if we do 2 to the negative 5th power, that's 1 over 2 to the 5th power, or 1 over 32. So, what would I have to raise 2 to get 1 over 32? That would be negative 5. So, this log is negative 5. Just like a lot of notations, we have a common logarithm. We define logs of base 10 to be common logs. So if I have a log with the base 10, I write it more simply as just log of x. And we've seen this kind of, leaving out of, or implication and other things. When we're talking about our radical notation, we know that if we see a root with no index, that it's an understood root 2, right? Otherwise, we have to put the index there. That's kind of the same thing we do here. Since logs of base 10 are very common, we just go ahead and say, all right, we're just going to leave that out and say log of x. And everybody's going to know that no base written in the logarithm, it's an understood base 10. Okay? So just know that if you see a log written without a base, it's an understood base of 10. And we call that the common log. Oh, I think I wrote that. Oh, so if you see a log written without a base, you should assume that the base is 10. So if I ask you to evaluate the log of 1,000, you say, oh, there's no base because there's no subscript, right? Always remember, subscript, the base is a subscript. So that must mean that the base is 10. So to evaluate, I have to think, all right, what am I going to raise 10 to get 1,000? Well, you can, if you don't know, you can play around in your calculator, but hopefully you realize that if you take 10 to the 3rd power, that would be 10 times 10 times 10, that is going to give you 1,000. Okay? Here, we want to evaluate the log of 1 over 100. So again, there's no base, so it's an understood base 10. And this is, very similar to the previous example, or a couple examples ago. I know that 10 to the 2nd power is 100. So therefore, if I do 10 to the negative 2nd, that's going to be 1 over 100. So if I'm trying to decide what am I going to have to raise 10 to get 1 over 100, that answer is negative 2. So the log of 1 over 100 is negative 2. The log of 275, again, that's no base. We've got an understood base 10. So I'm trying to figure out what am I going to raise 10 to get 275. Okay? If I play around with it, I know if I do 10 squared, that's going to give me 100. If I do 10 to the 3rd power, that's going to be 1,000. So for me to get 275, which is a value between 100 and 1,000, I'm going to have to raise 10 to a number between 2 and 3. What that number is, you don't really know. That number really is actually the log of 275. But when you're dealing with base 10, you can use the log button on your calculator. So again, we all have different calculators, but you should all see a log button, LOG, somewhere. So I can do the log of 275 in my calculator, and that tells me that it's somewhere, if I'm rounding that to the nearest thousandth, that's around 2.439. Okay? So this is approximately 2.439. And that makes sense with what I was thinking. Okay? So I encourage you, when you're working with logs, to try to reach for the calculator as minimally as possible. You know, you really want to practice your understanding. And yes, you know, you could find with a log of 1,000 is on your calculator, because any base 10 can be done on your calculator if it's all numbers. Same thing with this. But if you're always going to your calculator, you're going to reduce your understanding, which is going to make other things harder. Okay, so try to understand it as much as you possibly can. So that's the common log. We also have a thing called the natural log. And logs of base E, we call those the natural logs. So if we have log base E, we also have shorthand notation for that as well. We use ln. So rather than writing log base E, we write ln. Or vice versa. If you see ln, you need to know that that's shorthand for a log of base E. Okay? You should assume that it represents a log of base E. So if I ask you to evaluate the natural log of E, and this is something you're going to see a lot, you should be able to pretty soon see that and know automatically what the natural log of E is. But if we go through, work our way through the notation, the ln, natural log, is shorthand for log base E. And if I'm trying to evaluate a logarithm, I'm looking for what I need to raise the base to get the argument. So what would you raise E to get E? That would be 1. You would have to take E to the first power to get E. So the natural log of E is 1. Okay, similarly, the natural log of E squared, again, ln is shorthand for log base E. Our argument is E squared. So the question is, what do you have to raise E to get E squared? That is 2, right? You have to take E to the second power to get E to the second power. And then finally, the natural log of 147. So these were easy to do by hand because base E here and E in my argument, it worked out well. In this case, my argument doesn't have E. It's just a number 147. So I'm going to go ahead and reach for my calculator for that. And I can also do natural logs. So you should have a common log button, and then somewhere you should have a natural log button, the ln. So I'm going to type in the natural log of 147. And I see that that is approximately, to the nearest thousandth, 4.990. So this is approximately what I would raise E to get 147. Okay? Writing a logarithmic statement in exponential form, or a logarithmic equation in exponential form. This goes back all the way to the definition of a log on the very first slide, or second slide. Remember, saying that log base b of x equals a is the same thing as saying if I take b to the a power, I'm going to get x. And being able to go This is your logarithmic form. This is your exponential form. Okay? And being able to go back and forth between the two is going to help us out a lot when we're solving logarithmic and exponential equations. Okay? So this one, all it says to do is take this and put it in exponential form. So saying that log base 2 of x equals 6, we're saying that 6 is the power 2 must be raised to get x. Or that 2 to the 6th power is x. It didn't ask me to solve, it just said write it in exponential form. And that is what I've done. So I've said 2 to the 6th power is x. Okay? Here, this says solve this. And sometimes, you know, like I said, being able to go back and forth is really helpful. And what we find, one strategy that works really well for solving logarithmic equations is to start by rewriting that in exponential form and seeing if what we have is easier to solve. So if I have this statement, log base 3 of x plus 4 equals 4, I'm saying that 4 is the power 3 must be raised to get x plus 4. Or that if I take 3 to the 4th power, I will get x plus 4. In comparison, this equation versus this is something we know how to solve. We've been solving this since the very first day of algebra. Doing our simplification, 3 to the 4th power, that is 81. And now I just have this basic linear equation. To find out what x is, I can subtract 4 from both sides. And so I have x equals 77. Okay? So if we have an equation like this, we see how much easier it is to solve when I go from my logarithmic form into my exponential. We're also going to see sometimes when we're solving exponential equations that it's easier to put those working with logarithms instead. Okay? Looking at the same process, we want to solve this equation. And we're told that the natural log of x minus 5 is 2. Okay? ln, remember, is shorthand for log base e. So this is the same thing as saying log base e of x minus 5 equals 2. And like we were looking at in the last example, you know, if we go ahead and put it into exponential form, it might be a lot easier to solve. So if we're saying that log base e of x minus 5 is 2, that's saying that 2 is the power e must be raised to in order to get x minus 5. Or e to the second is x minus 5. Now remember, e is just that irrational number, 2.71, blah, blah, blah. So, you know, that is a number. X is my variable. That's what I'm trying to solve for. And so to get x by itself, I would need to add 5 to both sides. So we have x equals e squared plus 5. This is actually the exact value for x. Okay? But mostly in your homework, you are going to be asked to give a decimal approximation. But traditionally speaking, when we're solving an equation, we would never ever, unless we're dealing with an application, give a rounded solution. But just so you know what you're doing in your homework. So this really is the solution. This is what you would substitute for x for this statement to be true. But verifying, or I'm sorry, not verifying, but estimating. So for most calculators, your E button, remember, is above the ln. So in mine, it is. So if I hit my second and my ln, Then I get e2, and I can type in my 2, e squared plus 5. I see that that's approximately 12.389. Again, if I round that to the nearest thousandth. So that is approximately 12.389. This is the approximation. Okay? If you're trying to check your answer, if you substitute the approximation in, it's not going to check out. You would have to substitute the e squared plus 5 in for x to get this to be able to verify that this really is a solution. Last, we're going to talk about graphing logarithmic equations. So in the previous section, we looked at graphing exponential. So we already know how to graph exponential, so it might be helpful that when we're dealing with a logarithmic function, to go ahead and put it into exponential form, right? We know from definition, if we're told that the log base b of x is equal to a, that's saying that b to the a power is x. Okay, so if we have this logarithmic function, f of x equals log base b of x, just remember f of x is just notation saying that this is a function, and we can use that in place of y. So, it makes it a lot easier for most people to just replace that with a y. So that's the same thing as saying y equals log base b of x. And so if y is equal to log base b of x, then b to the y power is x. Okay? So putting my my logarithmic function into this form makes it a lot easier for me to find points, and makes it therefore a lot easier for me to graph. So to graph logarithmic functions, we will rewrite them in exponential form and then find points on the curve. Okay? So here we have y equals, I'm going to rewrite this. So this is the same thing as y equals log base 3 of x, and putting that in exponential form. So if we're saying that the log is y, we're saying that y is the power 3 must be raised to get x, right? Or 3 to the y power is x. So most of the time, we're used to, if we have y isolated, we then always just randomly substitute for x, or not necessarily randomly, we substitute for x and plug it in to find the corresponding y. Here, we have x isolated, so my point finding is actually going to be backwards. I'm going to input values for y and then find the corresponding x. And the values of y that you should input, you do it using the same thing. That first special point would be what would make this power equal 0. So that would be if y is equal to 0. And then I do a couple points up and down. So, because I'm on the y, right? Rather than left and right, I'm going down and up. So y is -1, -2. Y is +1, +2. So I'm going to put in my values for y to find the corresponding x. So if y is -2, I substitute that here. So that's 3 to the -2nd, which is 1 over 3 squared, or 1 over 9. So 1/9 is the x-coordinate that corresponds to a y-coordinate of -2. If I input the -1, I have 3 to the -1st, which is 1 over 3. So that is that x-coordinate. If I substitute the 0 for y, I have 3 to the 0 power. And remember, anything to the 0 power is 1. So substituting 0 for y, we find that the corresponding x is 1. And then substituting the 1 for y, we get 3 to the 1st, or 3. And substituting the 2 for the y, we have 3 squared, or 9. And so now, these are my points that I can use to make the graph of this logarithmic function. So I have an ordered pair at 1/9, -2. So write 1/9 down 2. Do the best I can here. Write 1/3 down 1. Write 1 up 0. Write 3 up 1. And write 9 up 2. And logarithmic functions and exponential functions are actually inverses of each other, or rotations about the line y equals x. So when you look at this graph, if you think about putting in more negative numbers, then the value of x is just going to be closer and closer to 0. So here, what we end up with is this vertical asymptote on the y-axis, or where x is equal to 0. And our function just hugs along that, and this continues to be an increasing function. Okay? So it has the same basic curvature, but a logarithmic function would be a rotation of an exponential about this line, y equals x. Okay? So, let me know if you have any questions. I would be happy to help.